Well, welcome. Hey, here we are backing up here on 7-5, second day of 7-5. Today we will focus in on the logistics growth. And what is logistics growth? That's what we're going to talk about. We did the partial fraction work yesterday, so now on to these logistics growth models. And let me page forward. That quick review, I think we're going to save the minutes on our video and not go through that. That should be something you can do anyway. Um, there is this law of natural growth, and the assumption goes that the population grows at a rate that is proportional to the size of the population that's present. So if I have a lot present, it will take off and grow quite rapidly because I'll have lots of starter stuff to populate. If I start with just a little bit, then it's going to be a little bit slower growth curve. So what does that translate into? Well, it translates into that rate of change. The population grows at a rate. So here's the rate that's proportional. Well, we've got to have a constant of proportionality and the size of the population. So there's the three, really the variables going on: the rate of growth, proportionality constant, and the population that was present when it started. We know that P of 0 can be written as P naught, or P sub 0, P sub naught. And if I take and integrate, separate and integrate, I would come up with P of t. So this is the ending population. P naught is the beginning population. And then e to the kt is that growth constant. We come up with what we've known as the growth model for quite a few years in math, right? You've been working with that. Sometimes we called it the PERT formula when we were working with principal, and we'd come up with some dollar amount at the end when we work with principal and interest. But it's all basically the same. So now what we'd like to do is introduce the fact that there's this logistics curve. The logistics curve is a common sigmoid curve given its name in 1844 by a person, looks like a French person, who studied it in relation to the population growth. And you can see how it is this S-shaped curve where the initial stage of growth is approximately exponential. And that would be the red line that we see, right? And if it were to continue, you could see how that would look like exponential growth. But then, as we start saturating the environment with the population, the growth begins to slow down. It's still increasing, but at a decreasing rate, okay? So it's got that slowing down, and that's what kind of bends it back over. If you analyze it from a concavity standpoint, we're concave up, where the population is increasing at an increasing rate, and then it turns into concave down, where the second derivative would be zero or negative, and so the second derivative reflects on the first derivative. That means my first derivative here is still increasing, general trend, but at a decreasing rate, second derivative negative. This point where they transfer over as it starts to begin getting saturated, that is where the growth starts slowing down. So concave up, switching to concave down, this is where the second derivative ends up being zero. It's an inflection point. Oh, let's add that to this. This is an inflection point. And the rate of change for the sigmoid curve is k times p, where this still is some constant of proportionality. P is population, and then I get P divided by capital K, which is different than little k, capital K. So as we look at this, there's a lot of observations that can be made, and I'm trying to remember if I need to make them here or if it comes, yeah, we might as well talk about them. Yeah, we might as well talk about them right now. So this point here we had as our inflection point. What happens as P and K get close to one another, as the population approaches K? Well, if P approaches K, as P tends to become K, then my rate of growth goes to what? Well, P divided by K would create 1. I'd have 1 minus P over K, which would be 1. And you guessed it, that goes to 0. So the rate of change goes to 0. And it starts flattening off up here. So this dashed horizontal asymptote up there resides at capital K. And I don't know if that looks like a capital K to you, but that's what I want it to be. That's a big capital K. That is known as carrying capacity. So as our population starts heading towards carrying capacity, it's really the population growth is going to become quite small, right? Because this factor inside the parentheses is getting smaller and smaller and smaller, because I'm taking 1 minus 0.9, 1 minus 0.95, 1 minus 0.99. That number is going very, very small. Rate of fastest growth, that is often an AP question. Usually the questions from the AP are somewhat simple, a little bit. It's mainly a lot having to do with the actual shape of the curve and what's happening at our curve. So at this inflection point, where we switch from concave up to concave down, this is the point where the rate is the fastest, where dp dt is greatest. It's got the greatest exponential growth at that particular point, because thereafter it's increasing but at a decreasing rate. So that's the point where dp dt is growing the fastest, or the population is growing the fastest. So P is growing fastest. Also, how can I identify that point? That is K divided by 2. It's half the carrying capacity. So that's where we can identify the population growing the fastest. Is it possible to have a dp dt that's negative? Yes, because it is possible that I could have a population that's starting above carrying capacity, and then it's going to come down into carrying capacity because the environment can't sustain that population, like a lake. A lake gets overpopulated in fish, and you'll have fish start dying off. Happens in the winter in the lakes, and you know what the limiting factor is sometimes in the lakes? The amount of oxygen present, because as the ice starts coming in, especially if you get a really heavy or cold winter where you get thick ice, you can have oxygen depletion, and it can't sustain all the population of the fish, and they'll start dying off. So there, your environment changed a bit, and you could be above, like your fish population could have then been above carrying capacity, and you'll come down into it. Sometimes that's a trick question on the AP, asking if dp dt is ever negative, and yes, it can be. It looks like it's always positive here, but it doesn't have to be. Also, sometimes you'll see a question, dp dt equals 0. When does that happen? And most of the time we'll say when P approaches K, because we see this relationship over here. 1 minus 1 goes to 0. The other time is if population equals 0. So there is no population, because then you can see this factor here. If P equals 0, then dP dt would equal 0. So the rate of growth is 0 because there's nothing present to get it started. That actually covers a lot of the AP type questions. It's all about the formula and the shape of the curve. So this picture here, what am I supposed to get out of this one? Oh, the fact that there are a couple different ways to write the logistics curve, the rate of growth. This is the one I just spoke to you about. We had capital K for carrying capacity, capital P for population, little k constant of proportionality. There are some textbooks that go with this version. So what does it say? Well, it's just arranged a little bit differently. This little k is still a carrying capacity. However, that little k and this little k in this particular formula, even if it was working on the same population, the growth population, they would not be the same k. Just because of the way the formulas are written, they would have to be a different k value. M is known as the carrying capacity in this one, and once again you would see as P approaches M, we could have dP dt heading to 0. So that one you can see again, as population tends to M, it would reduce the rate of growth. And we also could have a 0 if population was 0, then dP dt is 0. If population were equal to M, if I were at carrying capacity, dP dt would be 0, and we get that horizontal asymptote up there. This one, just different variables are really going on in that, where y is the population. So I think through analysis you can figure out what's going on. Logistics curve. Growth occurs when the rate of growth slows as the population approaches the maximal sustainable population. Moving on. Steepest growth rate, we talked about that inflection rate. That's M divided by 2, or carrying capacity divided by 2. In this case, they're saying M because they're using that other formula. This is carrying capacity. Yep, all right. This one is a nice little slope field, because from this we can create slope fields. When P is less than M, the growth rate is positive. When P is greater than M, the growth rate is negative, because you're coming in from above then. Population is greater than carrying capacity. Yeah, good stuff. Solve the differential equation. You know what? I am not going to have you guys do that, because that has never been a question on the AP test, and it's actually quite a process. But once I solve that, I should get something that looks like this, where I get P equals, because I'm solving the differential equation, dP dt. So I get populations equal to. This A down here is what gets confusing, and that is all based on carrying capacity and initial population. But we're going to pass on that, because that is really quite a process. And there it is again, but we're going to say heck no. All right, the logistics equation is given to us in the yellow here. Could you tell me what the carrying capacity is? Well, carrying capacity is when I take this rate down to 0, right? What would mathematically make that happen? When P approaches 1,000. So I know my carrying capacity is 1,000, and here you can see the horizontal line that the slope field is directed towards. Does T, time, impact the logistics equation? No, it does not. Notice that there's no time in our differential equation here. No T showing up. So it's purely based on population. When are the negatives, or when are the slopes positive and when are the slopes negative? Positive slopes, slopes that are positive, is when P is less than K, which means that P is less than 1,000. But it also has to be bigger than 0. So let's say that P is greater than 0, but less than 1,000. Get very specific there. When is it negative? When P is greater than 1,000. Because then I'd be above and I need to come down. Where is the equilibrium point? Well, if we just tried to draw in off of our slope field, we'd have a growth curve that looks like that. My fastest rate of growth is going to be at half the carrying capacity. So 1/2 of K, which means I'm really 1/2 of 1,000. And just looking at the curve, it does look like 500, doesn't it? That looks like where that bend is shifting. I'm from concave up, switching over to concave down. What do you notice about the slopes and the equilibrium point? The slopes and the equilibrium point. Well, the slopes start getting less steep after the equilibrium point, correct? Yeah, I've got steep slopes, and then they start slowing down. So slopes become less steep, or less positive would be a good phrase to use. Less positive after the equilibrium point. Approximately what population is there an inflection point? Well, if that were a question were asked to me, that population happens at 1/2 carrying capacity, 1/2 of K, or at 500, right? So a couple different ways you can come at that 500 number. Sketch the solution curve. So if P of 0, let's get this is good. At P of 0, we start out with 100 for our population. So then I would follow kind of jiggly here, something like that. What if I started at 400? Is my shape of my curve still the same? If I started at 400, I have just a tiny bit, and then I'm switching over from concave up to concave down. Because remember, our switchover point is at 500. So I have just a tiny, tiny bit of concave up, and then we hit that inflection point and switch into concave down. What if I started at 1,300? Oh, 1,300. We have way too much population. We cannot sustain this. So it must come down and reach carrying capacity. All right, good stuff. This little illustration is just talking about how we transfer over from our normal growth rate for exponential functions into a logistics growth curve. So if you want to read that, go right ahead. Another question here, these are AP style type stuff. We talked about the two different equations. So the growth rate of population P bears in a newly established wildlife preserve is modeled by the differential equation dp equals 0.008 P 100 minus P, where T is measured in years. But there's no T, it's just in relationship to T, right? If I were to separate and integrate, I would end up with T's in my original function, just not in the derivative function. So when I look at this function, it reminds me of that style, where M is the limiting factor, P is population, K is growth constant. Hopefully that's what you saw too. What is the carrying capacity for the bears in the wildlife? Well, as soon as P reaches 100, my dP dt is going to go to 0, isn't it? So the carrying capacity, I could call it M here, equals, oops, I almost wrote a 0. Takes the derivative to 0, equals 100. P approaches M, right? What is the bear population when the population is growing the fastest? Well, it's always at 1/2 the carrying capacity. What's the carrying capacity? Well, in this case, it's where the two values come together, so they come together at 100. So 1/2 of 100 is 50. What's the rate of change of the population when it's growing the fastest? So it's growing the fastest when P equals, look at P equals 500, right? So dP dt evaluated when P equals 500 would be 0.008 P times 100. Oh, I'm sorry, not 500. I was thinking 1,000. At 50, so minus 50, and that's where we're going to get our best balance of 50 population. That also, I should have substituted 50 in there. Let's switch that to 50. Just caught that. And yeah, so 50 times another 50 times a 0.008. Do I have a number on that? Because in my head, it turns out to be 20 bears. All right. And I think that was close. That's the end of my notes. Oh, I see the bears. I put in the moose. So in 1985 and 87, the Michigan Department of Natural Resources airlifted 61 moose from Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach carrying capacity in about 25 years, with a growth rate calculated out as shown. So I've got my carrying capacity. According to the model, what is the carrying capacity? Say it out loud. What do you think it is? I think it is 1,000. I tend to use K for my carrying capacity. So I'd say it's 1,000 right there, right? Just let P get close to K. With a calculator, generate a slope field for the differential fields. Done for you. Solve the differential equation. You can do this on Desmos too if you ever want to make a differential field. I think we did them last year, a slope field. Desmos does a really nice job. Just Google slope field on Desmos and you should come to an application where it allows you to put your formula in. Solve the differential equation with the initial condition P equals 61 and show that it conforms to the slope field. So, you know what? I don't have any numbers along here. However, I kind of do know that this must be 1,000 up here, right? So this would have to be around, I don't know if I hit halfway there, 500, 400, 300, 200, 100. So yeah, 61 has to be then kind of down right in here. Follow that. And that's our curve. And like I said, I don't think I'm going to have you do the solving on that because they just never do on the AP. All right. That is not the homework that we do. It is the AP free response questions, I believe, or they might be multiple choice. But there should be a worksheet following that's there for you to do. Have a good day.